So getting ready 12. At the beginning here, we're going to have to read probably 2 or 3 times through this original paragraph before you understand what it's saying. But it is saying we have one man, Bob Cooper, who was born in 1890. 40 years later, by 1930, he has 3 sons, all named Cooper. Another 30 years go by, so 1960, each of those 3 boys had 3 sons of their own. Another 30 years, all of those sons each had 3 sons of their own, and so on and so on. So the first question asks, how many Cooper sons were born in that 30-year period between 1960 and 1990? Now, before we should answer that, or before we can even attempt to answer that, I feel like we should jump ahead and try number 2, which says to create a diagram to show this pattern, because that's how I would figure out number 1 anyway. So let's just start down here and say, okay, in 1890, we had Bob Cooper. That dot is Bob Cooper. He has 3 sons. So this is by 1930. There are 3 Cooper sons. Each of those 3 are going to have 3 of their own. So here's 3 more sons from this guy, 3 more sons from this guy, and 3 more from this last son. So by 1960, there are 1, 2, 3, 4, 5, 6, 7, 8, 9 sons have been born in that year, those 30 years between 1930 and 1960. Now, if we continue that pattern, and I'm not going to draw all of these dots for the next generation, but by 1990, each of these orange dots will split into 3 more sons. Okay? Each orange dot turns into 3 green dots. So by 1990, or in that 30-year period, 1960 to 1990, those 9 orange dots become 27 green dots. Okay? So if we look at the pattern here, the orange generation, there were 9 sons. The purple generation, or the second generation here, there were 3. And back in 1890, there had only been 1. So if we look at the pattern of Coopers, we start with 1. Next generation, there's 3. Next generation, 9, then 27. We see that this is exponential. It's multiplying by 3 every 30 years. Okay, so how many Cooper sons were born in the 30-year period between 60 and 90? That's from orange to green. There were 27 Cooper sons born in that 30-year period. Number 2, we've already done. We have our diagram. Number 3, predict how many Cooper sons will be born between 1990 and 2020 if this pattern continues. Well, 2020 is the very next generation. So those 27 green sons would each split into 3 of their own. So if we multiply that 27 by 3, that generation ends up with 81 Coopers. And then number 4 says take this one step further. If we go from 2020 to 2050, well, that 81 times 3 again is 243. So we know our answer is 243. But number 4 actually says to write an equation that would help us predict that. Now, we got an answer without an equation. But we know how to write equations for exponential. They have to look like y equals a times b to the x, where a represents the y-intercept, or our 0th term. B is our common ratio, or in other words, our multiplier. And x is how many times we are going to multiply by that common ratio. Well, in this case, we multiply by that every 30 years. So it's actually going to be number of generations. Okay? So our equation would be y is equal to our y-intercept, our 0th generation, was Bob Cooper himself, so 1 times our common ratio, each generation we're multiplying by 3, so the b is 3 in this case, and then to the x power, x again standing for number of generations. Well, that 30-year period from 2020 to 2050 would be the, let's see, there's 1, 2, 3, 4. We're talking about going to the 5th generation. So if we were to put a 5 substituted in for x, this becomes y equals 1 times 3 to the 5th. 3 to the 5th is 243 times 1. We get our same 243 that we found using our diagram. Now, numbers 5 through 8, we are going to substitute the values 1, 2, 3, 4, and 5 into each of these equations. So I'm going to go ahead and set up my table with the x values, and we just one at a time substitute each x value into the equation. So 4 to the first would be 4. When I put a 2 for x, 4 to the second is not 8, but 16. Substitute a 3, 4 to the third is 64. 4 to the fourth is 256. And 4 to the 5th power is 1024. That's really just a calculator exercise. Okay, numbers 6 and 7, if you look at both of them together, they're very similar looking. Only difference is number 6 has parentheses, number 7 does not. That makes a huge difference. So again, if you're using a calculator, you want to put this in exactly the way you see it on the paper, okay, with the parentheses or without. So let me try to show you the difference. When I have the parentheses in number 6, then -3 to the first is just simply -3. Parentheses don't seem to matter at all. When I have -3 squared, that actually means the entire -3, including the negative sign, is squared. So it's -3 times -3, which is 9, positive 9. The two negatives became positive. -3 to the third, again, the entire -3 is multiplied by itself 3 times. So -3 times -3 is 9, times another -3 is -27. Okay. When I do -3 to the fourth, that's -3 times -3 times -3 times -3. Well, the first two become positive 9. The next two become positive 9. And 9 times 9 is 81. So you can kind of see what's going on here. When there's an odd exponent, we end up with a negative answer. But when the exponent is even, we have an even amount of negative signs, which turn in each set of 2 turning into a positive. So your overall answer becomes positive. Odd exponent, negative. Even exponent, positive. So -3 raised to the 5th power, there would be a total of 5 negative signs, resulting in -243. Now, that is different from number 7, where there are no parentheses. So in number 7, when we put 1, 2, 3, 4, 5, when we substitute 1 for x, that's -3 to the first. Well, only the 3 has the exponent on, not that 1 is doing much, but it's only with the 3, not with the negative sign. So my answer is -3. What's the difference, you may ask? Well, when I put a 2 in for x, -3 squared, again, only the 3 is being squared. So this is a negative sign, and then 3 times 3. Well, 3 times 3 is 9. Put a negative in front of it is -9. When I do -3 to the third, that's a single negative sign, and then 3 times 3 times 3. -27. Negative 3 to the fourth is a single negative sign, and then 3 times 3 times 3 times 3, negative 81. So the difference here, we get the same numerical value as we did when we used parentheses, but all of the answers are negative because the negative sign does not get repeated. There is one negative sign. It does not have anything to do with the exponent. You tack it on at the end. All right, and number 8, the simplest one, we're raising 10 to powers 1, 2, 3, 4, and 5. Well, when you raise 10 to a power, the exponent simply tells you how many zeros are in the number. So 10 to the first is 10, 10 squared, so 10 times 10 is 100, 2 zeros. 10 to the third will have 3 zeros, 1,000. 10 to the fourth is 10,000. And 10 to the fifth, 100,000. Okay, numbers 9 through 12 are some equations to do, should be a review. So we're going to split into two sides and isolate the variable x. So I see in number 9 that I have parentheses on both sides, so I'm going to have to distribute on both the left and the right. So that becomes 3x minus 3 equal to 2x plus 6. I have variables on both sides, so I look for the lower amount of x's. Here's 3x, here's 2x. So I'll try to eliminate the smaller amount, which is the positive 2x. Subtract 2x on both sides. 3x minus 2x is 1x, or just x. The negative 3 still sitting there. On the right-hand side, I still have a 6. Get rid of the minus 3 by adding 3. So x is equal to 9. Number 10. This time I have parentheses on just the left-hand side. So I will be distributing over on the left here. 7 times x is 7x. 7 times 20 is 140. That is equal to x plus 5. Again, we have variables on both sides. I choose to eliminate the smaller one. So to get rid of 1x, I will subtract x. 7x minus 1x is 6x. I still have plus 140, and I still have equals 5. I will get rid of the positive 140 by subtracting it on both sides. So 6x is equal to negative 135. Now, back in your younger days, you would have said, hey, I can't divide both sides by 6 because 6 doesn't go into 135. We've grown out of that now. We know that every number can divide every other number. So x is equal to, it's going to be negative. And if we reduce 135 over 6, let's see. 3 can go into both of those. So 3 goes into negative 135 45 times. Divide 6 by 3, it's 2. So either negative 45 over 2 or negative 22.5. Since that is a terminating decimal, you are welcome to use the decimal value. Number 11. Again, parentheses only on the left, so distribute the left-hand side. 9 times x, 9x. 9 times negative 2, negative 18. Equals 3x plus 3. X is on both sides. Let's eliminate one of them. I choose to get rid of positive 3x, so I'm going to subtract 3x. 9x minus 3x is 6x. Bring down minus 18. Bring down the 3. Get rid of negative 18. We need to add 18. So I'm left with 6x equal to 21. Divide both sides by 6. x is equal to, now again, 6 doesn't go in neatly to 21, but it goes in 3 times with the remainder of 3, so 3 over 6 is a half, so that is 3.5, or had you just reduced the fraction, 7 over 2. And lastly, number 12, do not skip number 12 because it has fractions. Fractions are not frightening. Distribute on both sides, so 2 times a is 2a. 2 times negative 1/3 is negative 2/3. 2/5 times a is 2/5 a. 2/5 times 2/3 is 4/15. We have variables on both sides. I need to cancel one of them. I choose the smaller one, so I'm going to cancel the 2/5 a. Now, I don't want to try to do that reciprocal method to get rid of the 2/5 because I'm trying to cancel the entire term, not just the coefficient. So I need to either add it or subtract it. Since it's positive, I need to subtract 2/5 a on both sides. Now, if you have a calculator, this is not difficult, 2 minus 2/5, but let's go over here on the side and remind ourselves how we do that if my calculator batteries are dead. So this is really 2 over 1. I need common denominators. The common denominator for 1 and 5 would be 5. So both of these fractions need to end up with denominators of 5. This one doesn't need to change. If I multiplied that 1 by 5 to change this denominator, then I have to do the same to the numerator. 2 times 5 would be 10. So 10 over 5 minus 2 over 5 is 8 over 5. So I am left with 8/5 a. I still have minus 2/3. And on the right, I have 4/15. Okay, now I need to cancel the constant here, which is minus 2/3. So I will add 2/3. That leaves me with 8/5 a equal to, now once again, calculator would make that real simple, but 4/15 plus 2/3. Common denominator for 15 and 3 is 15. So we leave the first fraction alone. The second one, since I multiplied this denominator by 5, I need to do that to the numerator, becomes 10/15. 4/15 plus 10/15, 14/15. And now my last step is to eliminate the 8/5, and this is where I can multiply by the reciprocal because I'm trying to cancel just the coefficient, not the entire term. I want the a to remain where it is. So doing this reciprocal method, 5 times 8 is 40, 8 times 5 is 40. So that really becomes 40 over 40, which is 1. So I'm left with 1a, just as I had hoped from the beginning. On the right here, 14 times 5 is 70. 15 times 8 is 120. To reduce 70 over 120, divide them both by 10, we get 7/12. Now for this one, do not try to change it to a decimal. It's a repeating decimal, and we don't use those when we can write them as fractions.